Hello and welcome back to the second video where we were solving the heat equation via separation of variables. And let me just remind you what we were doing. So we wanted to solve the equation, so what we did was we used a trial solution which we call an ansatz. We said the trial solution was a function of x multiplied by a function of t. Then we inserted our Dirichlet boundary conditions divided by x times t, the functions, to get two ordinary differential equations. Then we had three cases. So case 1 was that lambda was equal to 0. Case 2 was that lambda was positive. And case 3 was that lambda was less than 0. And the only case that was non-trivial was case 3, where we got this solution here. Okay, so now we have to find out what the values of mu are. So now we have this solution. Actually, we don't know the solution is non-trivial, but I do, so I will show you why that is. So now we'll insert our initial boundary conditions into this equation. So firstly we have, when x is 0, we have that a is equal to 0, since cosine of 0 is 1. And then we have when x is 2, we have this case. Now, either b is equal to 0, and then we will have another trivial solution. So that's no good. B can't be equal to 0, otherwise we would just get 0 equals 0 again. So we must have that sign 2 root 2 times mu is equal to 0. So what's the solution to this? So we know the solution to this equation is when the argument, say x, is equal to some integer multiple of pi. This is by drawing the graph of fx equals sine x. And we can see that the roots are integer multiples of pi. So this tells us that 2 root 2 times mu is equal to an integer multiple of pi. Hence, mu is equal to 2 root 2, n pi over 2 root 2. But here we will consider n to be a natural number. We will look at why this is the case. So, we've now found a value for mu. So we can go back up to the original ODE, number 1, and we can insert mu. So, the ODE was this. So let's copy this and solve the ODE. Okay, so let me just rewrite this to make it a little bit neater. So we're now left with a first order homogeneous differential equation, and these kinds of differential equations are not too hard to solve. So what we do is we take a integrating factor, which is equal to e to the power of the integral dt, which is equal to e to the power of n pi 2 root 2 squared t. And then we multiply both sides by this, and then we get d by dt of t multiplied by e to the power of n pi over 2 root 2 squared t is equal to 0, which follows that t is equal to some constant value times e to the power of n pi over 2 root 2 squared t, and this is negative, okay, because we've divided by e on the left hand side after integrating. Okay, so you integrate and with respect to the t, and you're left with that. Okay, so that is the solution for t, but we know that the whole solution for the PDE is equal to the function of x times the function of t. Okay, and if we go above, we've got the function of x now, so this is equal to, we go up and we have, so the general solution for the value of x is b times sine of 2 root 2 times mu, which is n pi over 2 root 2. Which of course cancels out, multiplied by a e to the power of minus n pi over 2 root 2 squared t. This is a general solution, an nth solution. However, one solution of a PDE, if you add another solution, that also becomes a solution. So that for the general solution, we absorb the constants, because a times b is just another constant, so we absorb the constant into a, to get this, and the constant b has been absorbed into a times b. We just rename it as a again, but it's just the constant a times b. So this is our general solution. But if you remember, we have initial conditions. Okay? We have initial conditions. Oh, and of course, with the general solution, I forgot to say, it's the sum of each nth solution. So remember, n is a solution. So when n is equal to 0, you have a solution. Really, I should say n is equal to 0, but n pi times 0 is just 0, so n goes from 1 to infinity. Okay? And we will insert our initial conditions. Now, this fact here is important. The sum of the solutions. It's called the superposition principle. And is an important fact in study of differential equations and partial differential equations. Okay, so now we will insert our initial conditions. And so we go to firstly, and this is our initial condition. So let me just copy this. Okay, so now we can use our general solution and put in 0 for t. So what do we get? So we have that on the left-hand side, the sum n is equal to 1 to infinity of a times sine n pi x. Now 0 is equal to t here, so this vanishes, so we're just left with the e to the 0 just vanishes and goes to 1. So that is what we're left on the left-hand side, and on the right-hand side we are left with this. The sum of sine terms. And if you're familiar with PDEs, these are orthogonality relations. They come from something called Sturm-Liouville theory, but we won't cover that today. And they are orthogonality relations. But here we can just directly compare, since we don't need to do something called the Fourier series. So, if we compare here, we can see that when n is equal to 1, we have, so when n is equal to 1, we can just directly compare. We have that, actually, let me just write this out. So we have a times sine pi x plus b times sine 2 pi x plus c times sine 3 pi x, etc. is equal to sine of pi x over 2 minus sine of pi x plus 4 times sine of 2 pi x. And I just noticed at this stage that I'd made a slight arithmetic error. I was missing a factor of a half on the bottom of each of these we call eigenfunctions, which are solutions to individual solutions to the PDEs. Anyway, so on the left hand side I've started to write out the infinite sum, and also I forgot to mention the infinite sum, they have these a's because these are different constants in front of each of the solutions, and I've labelled them a1 up to, well, a4, but they go on forever. So on the left hand side I've written these, and on the right hand side I've written the initial value when you plug in 0 for t. And notice here that there is a pattern going on. So on the left hand side we have a1 times sine of n pi x over 2. On the right hand side we have sine of pi x over 2. So we can just compare coefficients here. So we can see by comparing coefficients that a1 is equal to 1. Also we can see that a2 is equal to minus 1, a3 is equal to 0, a4 is equal to 4, and an, where n is greater than 4, is equal to 0. So we've now found the 4 coefficients. And so here I've just written the general solution of the PDE, which is the sum of the what we call eigenfunctions. Okay, and in a future video we'll cover what an eigenfunction is and corresponding eigenvalues, and they have similarities with linear algebra, but they're not the same. Thank you for watching. So in the further videos we'll look at the wave equation, so Laplace's equation, and PDEs under non-square boundaries, domains. Thanks.